This week, we're going to be diving in to the very basic building blocks of life and talking about the chemistry behind the structures that form our bodies, that power all of the reactions of life, and that we rely on. We're going to do a broad overview of some basic facts about chemistry. We're going to talk about the role of water, which is a really important substance, but often we don't really stop to talk about why it's so important. We're then going to talk about the role of carbon and what organic molecules are. From there, we're going to move on to biological macromolecules, the large, complex substances that actually form most of the building blocks of our bodies and most of the food we eat and provide the energy that we need to get through life. So this is going to be covering quite a bit of ground. Hopefully it won't be too difficult. There's a lot of overlap, obviously, with chemistry, but even with physics in this section. So we're going to focus on what's relevant to biology. But I really encourage you that if you find any of these topics interesting, to dig more into them, because it really is fascinating. And one of the themes you will see over and over again is just how some of these, you might think minor properties of atoms and molecules actually are what make them do the things they do. So let's dive in. I realize that not everybody who is enrolled in this class has necessarily taken a chemistry class, or maybe hasn't taken one in a long time. That's totally all right. We're not going to dive too deep into a lot of these concepts, but it's really important that you remember a few terms and facts about how atoms and matter and elements all work for the rest of this unit to make sense. Let's start with the basics. What's matter? Well, matter is stuff. It's anything that has mass and takes up space. It's all of the things you can see. It cycles through Earth's ecosystem and is transformed into different compounds and used in different systems and reactions. But with very few exceptions, little of it enters or exits Earth as a whole. Matter is made out of atoms. Atoms are the smallest cohesive single unit of matter that can be identified as a specific element. Obviously, there are subatomic particles, things that make up atoms. But the smallest unit that you can go to, where it still has the chemical properties and identity of a given element, is the atom. Atoms are made of protons, neutrons, and electrons. And all of these are defined by what charge they have. So in the center, what's known as the nucleus, the protons, which are positively charged, you can remember the P for positive, they are clustered together with the neutrons, which do not have a charge, into the nucleus. The number of protons is what determines what element a given atom actually is. If you look at the periodic table, those numbers that define where an element sits on the table, that's how many protons it has. And while the neutrons and protons do some really interesting things, they're very much in the realm of chemistry and physics and beyond the scope of this class. In general, what we're talking about when we're talking about the chemistry of life are these smaller atoms in the first couple rows of the periodic table. The bigger atoms get, the harder it is for that nucleus, all those protons and neutrons, to actually stay together, and that's when things start to get spicy, by which I mean radioactive, because they can't physically hold together when they get larger. So it's probably not a huge surprise then to hear that almost everything you are going to be using in your body has a relatively small number of protons making it up. Now, electrons are the third type of particle, and these are negatively charged. And one simple way to think about it is that the actual chemical properties of a given element largely derive from the number and arrangement of electrons in that atom. So protons determine things about how the atom kind of works in terms of the physics and things like radiation and all that stuff. The neutrons determine mass, but it's the electrons that actually determine, is this a metal? Is this a relatively stable element like carbon? Or is it something like sodium that reacts with the slightest bit of water near it? These are determined by the electrons. Electrons are there, then they're kind of like the little knobs on a Lego. A Lego, if you think of it, is just a little square brick, but it builds on to form larger things with those little nubs on them. If anybody knows what the technical term for what part of the Lego that is, I would be very interested in knowing, but we're just going to go with nub for now. Just like those are the actual unit of the Lego that determine how many other Legos can stick to it and the sort of things you can build with it, the electrons in an atom are what determines how many other atoms it can stick to, how it sticks to them, and then what sort of molecules can be formed. Molecule is just a fancy way of saying combinations of atoms that are relatively stably stuck together. You might have seen electrons depicted as each kind of in their own little orbit in that classic retro atom design. And this isn't really accurate, or even a little accurate. Electrons do orbit the nucleus of the atom, but they don't do it in those nice individual paths. Instead, electrons occupy what are called orbitals, and these are determined by the amount of energy in the electron. Again, really interesting stuff about this, but that's literally getting into quantum mechanics, and you're here for intro bio. So they're not randomly distributed around the nucleus. They come in layers, much like onions or ogres. At the basic level, you have what is called the s orbital, and this is really close to the nucleus, and it can only fit 2 electrons. The next orbital can fit 8 electrons. And this is the level at which a lot of the reactions and the compounds we're going to be talking about, where all of that chemistry is actually happening. See, the electrons in an atom don't just kind of randomly fit in there. They fill the orbital in a predictable fashion. An atom that has a full outer shell of 8 electrons will have 4 pairs of 2. However, when the orbital is filling, each of those positions that would be occupied by a pair when full is first occupied singly, and then when there are no more single positions left, then they start to pair. Again, there's some very interesting chemistry and physics reasons for this, but the main thing you have to know in terms of biochemistry is that number of unpaired electrons in that outer layer, which is usually going to be between 1 and 4, is what determines how many other things can bond onto that atom. This is what makes carbon so special. We're going to dig into that a little bit more, but first let's talk about what those bonds actually look like, because that will help us understand just why carbon's so cool. When you have an atom that has these unpaired electrons, a few things can happen. The simplest type of compound is what's called an ionic compound. Things like table salt, where you have sodium ions and chlorine ions. In this case, one of the chlorine atoms literally strips away sodium's unpaired electron in its outer shell. This leaves you with equal parts of positively charged and negatively charged molecules, or in an ionic substance. These tend to be really good conductors of electricity for that reason. It also means that they dissolve readily in polar substances like water. But as you can tell from that description, this is kind of a limited chemical setup. There's a lot of things that can be done, and indeed, things like our nervous system are very much determined by the flow of ions and charged particles and these sorts of compounds. But that's not what most of the compounds that we think of and that are important in biology are made of. Instead, these are made up of what's called covalent bonds. In this case, instead of one of the atoms stripping the spare electron away completely, instead, they kind of smush together and share an electron. This is what, for instance, makes up a water molecule. The two hydrogen atoms, which each have one unpaired electron, nestle up nice and close with the oxygen atom, which in turn has two unpaired electrons. The electrons then kind of just use both orbitals. Why do they do that? Again, chemistry. It's weird. It's fascinating. It's also very hard, and there's a reason I'm a biologist and not a chemist. Those covalent bonds are what make up the vast majority of molecules important in biological functions. In our next videos for this week, we'll get into more of just what these molecules are and what they do to power the processes of life.